We're doing chapter 7 in the book, and we're talking about light. So we're going to start now. Okay. So how fast does light travel? At the speed of light. And that number is about 186,000 miles per second. Oh, I thought 186,000 miles per hour would be fast. How about 186,000 miles per second? They have a laser beam they can fire at the moon, and astronauts have put a special mirror on there, and pretty much you shine the laser beam there, it's coming right back at you. Whatever angle you hit it at, it's coming right back at you. They do that all the time, and they know within this distance, they know within an error of 8 centimeters how far the moon is right now. Okay, it takes less than 4 seconds to it's back. The speed of light can go around the Earth about 7.5 times in 1 second. That's pretty fast. The sun, how long does it take the light from the sun to get to the Earth? 8.33 minutes. Ooh, what? It must be pretty far away. It is. It is pretty far. 93 million miles. It's far away. At the speed of light, it still takes over 8 minutes to get here? That's right. Ooh, it's pretty far away. Okay, so it travels the speed of light, and but what's interesting is, and Einstein said that's a constant, and so far we've never seen the speed of light not be constant. I had trouble with that too. If I throw a baseball at 80 miles per hour, and relative to the Earth, and then you put me on a moving train. Let's say the moving train's going at 100 miles an hour, and you have a flatbed, and I throw my 80 mile an hour ball. Relative to the train, it's still going 80 miles per hour, but relative to the ground, what's it doing? 180. But we have never noticed that with light. I can't explain this to you. If you have light travels at the speed of light, you put in a jet going at 1,200 miles per hour, then what's the speed of the light now? It should be the speed of light plus 1,200. It's not. I have trouble explaining that. And even Einstein said, no, that's a limit. It's a limit. Now, Star Trek gets away from it because what Star Trek does is it creates a warp field around the ship. And the warp field says we are immune to that. We can travel faster than the speed of light within the warp field and then come out of it. And that's how they get around that. And maybe we will. Maybe we will decide that we can do that. They also don't want you to travel the speed of light, come back later, and everybody you know is dead because it's been 200 years and it's only been 2 hours for you. So they make all kinds of concessions for science fiction and stuff like that. But we'll see how many of those come out to be true. All right, well, anyway, we know also that light can travel with different wavelengths. Is everybody okay with wavelength being the distance between two identical parts of a wave, like crest and crest, or trough and trough, or halfway down the mountain, halfway down the mountain? Whatever it is, that's called the wavelength, isn't it? And that they have a symbol for that. It's called lambda. Lambda is wavelength. They use a little lambda. Can you see a lambda here? Lambda looks like one of these. Okay, so wavelength is used there, and this guy has a bigger wavelength, this guy has a smaller wavelength, and this guy has the smallest wavelength. Okay with that? So light travels at the speed of light, all of it travels at the same speed, but they have different wavelengths. Okay, so that gives me to my first thing here. Wait a minute. If you travel as fast as I do, then how many peaks would come by a certain point per second? Ready? Let you go. Going at the speed of light. Which one would have the higher frequency? Frequency means how many waves per second. Right. If they're both traveling at the speed of light, you'd have more waves per second. And that's called frequency. Frequency, the funny thing, the units are called s to the minus 1. That means per second, doesn't it? Whatever, events per second. See that? Events per second. In this case, it would be what? Waves per second. And that's called frequency. Okay, so what's the relationship between wavelength and frequency? If you come over here to, here it is. Next page, I circled it for you. C is the speed of light. Does everybody know that? Little c. Little c is the speed of light, and they like that. They're gonna keep it that way. Equals lambda times nu. This is a wavelength times frequency. And how are they related? Remember back in physics? Directly? They're if they're inversely proportional. So if the bigger, the larger the wavelength, the what? The bigger the wavelength, what? The smaller the frequency. Okay, what about the smaller the wavelength? Okay, now the reason I need to know that is because there's a direct relationship, direct proportionality between frequency and energy. You got high frequency, you're high energy. So which one of these would be a higher energy form of light? Which one has high frequency? That has high energy. Now, that's what the quantum model is based on. So if I lose you there, I'll lose you for the next 2 days. Yes?
Doesn't light, the intersecting waves of electric energy and magnetic energy, they follow that zigzag, right?
Yeah, we say they travel in waves. We have to be careful about this because they always show what they call mechanical waves. Mechanical waves means it's in a material. Like if I had a ruler, and I go, I can hear that noise right there, and that wave is actually sound, air being compressed and not compressed. Compressed. I hear a noise. See that? And that's a mechanical wave because it had to move through a material. The ocean, the water never does come to you when you stand there. Watch that wave. Watch that wave. Oh, it made it all the way to my feet. No, it didn't. That water stayed out there. The water was at your feet to begin with. Somebody got splashed up on your leg. That water didn't come out there. Oh, I don't believe it. Well, put something out there. Let it float in the water. See if it comes toward you. I'm not saying it can never come toward you. I'm just saying that it's the energy that travels through the water. That's what's happening. And so the problem is these are called mechanical waves because they have to travel through something. You see that? But what is this kind of wave? What's it travel through? Nothingness. This wave is called electromagnetic energy. It can travel through nothingness. You get that? That's one thing you got to be careful about. The only thing they have in common is they do have wavelengths. They have frequencies with mechanical waves, and you can understand mechanical waves. You know, tie a rope onto the doorknob and yeah, you can make a wave, can't you? But did the rope from my hand go to the doorknob? What? I saw something go to the doorknob. It wasn't the rope. It was the energy traveling through the rope, wasn't it? Yes.
So if it does follow that kind of model, then doesn't it have one speed where it is the speed of it moving forward, but then there's also the speed of it taking that shape? Because if it weren't taking that shape, if it were moving in a straight line, it'd be moving faster.
Well, that's a good question. If I had that rope like this, could I take a video of the wave moving to the doorknob, and could I actually figure out how long it took? Could I figure out how long it took for that wave? And I would still call that the speed of that wave. So I would just watch the top of the wave, keep watching it. It would go to the doorknob, and I could figure out the speed. So I think some of your questions are good. I don't know all these answers. I don't know all the answers, like, why is a wave something that happens anyway? Right now, light, they think travels like this. It travels like this, and it travels like this, and it travels like this. See that? So it travels in every direction. Remember that day I had did I show you the polarized filters? Did I do that? Are you sure? Oh. Hey there. I didn't show you these?
Oh, yeah, you know.
Okay. Remember I borrowed them? Okay. But anyway, So what happens is, so one of these has a filter that only lets maybe this kind of light hit my eye, and this one only this kind of light hits my eye. So I watch. There's two movies going on at the same time, and so this eye gets this movie, and this eye gets this movie, and they're made two different cameras, and it makes it look like 3 dimensions. It looks like real, because this eye sees a slightly different picture than that picture. But then I think I showed this to you before. If I were to take this and line them up, you can still see through the light, but if I rotate it, then I could eventually block out, whoops, there. I could actually block out all the light. I don't know if you can see that very well. Can you see that? So anyway, so light actually travels in every direction unless it's polarized. Polarized light would say, I'm going to eliminate a lot of light and maybe only look at one type of light at the same time. So we look down here, and light, as far as you're concerned, every time I look at a shirt or whatever, everything that I can see with my eyes, that's it. Those are the wavelengths or the frequencies that my eye can send a signal to the brain and said, red, green. And we were taught to say red when we saw that. Yeah. Anyway, so this form of light here is called visible light. This is a visible light spectrum. That's where Roy G. Biv comes from right here. Get that? So reds are the big wavelengths, and we did that before. Remember spectrophotometry from between 400 and 700 nanometers? Okay, and red is near the 700, and blue is kind of the 400 nanometers. But what if we go smaller than that? We get to some really types of light. This is light. We have ultraviolet, X-rays, gamma rays, wavelengths that are incredibly small wavelengths, which means they're what? Very high what? High frequency, which means what? High energy. These will hurt you. These will hurt you. When they pass through your body, they will ionize, they will knock electrons all over the place, and they can kill lots of cells, and these are the ones that can hurt you a lot. Now, we go the other way, the wavelengths get very long, very long. Matter of fact, what is that, 10 to the 4th? Yeah. Can you imagine a wavelength that is 10,000 meter sticks long? The top of one wave, 10,000 meter sticks later. It comes up. Those are some really long wavelengths, and they're also low energy. I'm not saying they can't hurt you. That's a good question. But we have a lot of your cell phone stuff is in here. And there are studies. Some people think cell phone light, cell phone energy coming all this stuff is hurting us. I'm sure that they put a few $1 billion into anti-advertisement on that. I don't want people to think that cell phone radiation, I don't want people to think that kind of light's hurting people, because we're making lots and lots of money on cell phones. So that's about the last thing I want you to think about. So I don't know. I can't tell you whether cell phones are hurting or not. I do know that police people who do radar guns, whether it's true or not, there's a higher than normal rate of cancer, and especially in their hand area. And they have these guns. They fire radar, which is essentially, where's radar? I don't know the wavelength. I forgot. Anyway, there is evidence to show maybe that they're being exposed to a type of light that may be causing cancer. We'll have to see. So we'll see. If that's true, they're going to change the way they do the radar guns. Okay on this? All right, so now, go over here. This is the first mathematical equation you would use, and we already talked about that. If I told you the speed of light, and that's a constant, this happens to be in meters, it's about 300,000 meters per second. Think about that. No, kilometers. This is, what is that? 8, okay. This is meters per second, and if I change it to, that's about 300,000. Yeah, 300,000 meters per second, that's right. Well, anyway, that's a constant. So if I gave you the speed of light and I gave you the wavelength, you could divide and find the frequency. Okay, so look over here, look at the math, and you'll see how they cancel out, and you'll get s to the minus 1, and that's frequency. And so, does anybody know? I just circled it. what units are used to measure frequency? It's called hertz. And a hertz is per second. What does hertz mean? Per second. Seconds to minus one. Your computers, and I'm not a computer person either, but when you buy a computer, doesn't it tell you something about megahertz? Who's a computer person? What is it? Give me a number. Can you give me a number? And that has to mean the frequency at which information can be passed through there. And so, is there a special name for that in computer lingo? What do you call it? Speed? What do you call it? What do you call it? Hertz. Okay. And matter of fact, the hertz are so high, they're like, what's megahertz mean? Mega is million, isn't it? That's millions of hertz. See that? Millions of things per second are happening. Anyway, all right, so then we go to, let's go on to the next one. Here's a guy, recognized Einstein, and he's bothering him a little bit about the nature of light and stuff like that. And even back in Isaac Newton's day, the argument started even before Isaac Newton, but in the 1600s, 1700s, what is light? And there's experiments that show, I want you to imagine that I have a post in the ground and I have a target behind it, okay? And let's say I have an automatic BB gun. I won't be so violent today. I have an automatic BB gun. And I go, okay. Now, I remove the post, and what is behind the post is a part of the target that never got hit by a single BB. You get that? Didn't the post make like a shadow? And I saw BB dots everywhere except where the post is, right? Well, that means that what was I firing? Was I firing a particle or a wave? A particle. Now, if you go to the beach and you see a post in the ground, a wave comes by, a little gentle wave, nice gentle wave. What does a wave do when it hits a post? Brrr. What does it do? It bends around it. So if you saw that post in the ground, I shot something out of my gun, and you saw it hit the target behind the post, that means something bent it, isn't it? And it must have been a wave I was shooting. So here's the problem. Even in not Newton's time, even in Newton's time, we had experiments showing that light had to be a particle. It had to be. But then you had other experiments showing what? It had to be a wave. And there were arguments back then about what is light? What is light? And guess what? 100 years later, what is light? What is light? In early 1900s, what is light? What is light? Well, you're not going to like the answer, but they think they figured it out. Which one is it? It's both. Now, that sounds like a politician, doesn't it? I'm not gonna say it's a particle because I know you're gonna bring up the experiments that shows. I'm not gonna say it's a wave. It has a dual nature. The theory is it has a dual nature. It's a particle and a wave at the same time. You like hearing about this kind of thing? Well, sort of. Well, Einstein does some experiments, and a matter of fact, he won a Nobel Prize on this one. And does anybody know about? Have you ever read about the photoelectric effect? Okay. So what he did is, let me see if I can read this. So what he does, he takes light and he has a piece of metal, and he's shining light on it, and he's trying to figure out whether or not any electrons are jumping off of the metal. Can light cause electrons to be excited and go away? And he finds out that if he takes one kind of light with a certain frequency, a certain wavelength, and he shines it, and it gets more intense and more intense, not a single electron leaves the surface. Then he takes another wavelength, and he shines it at a low intensity, and electrons start jumping off. What happened there? One wavelength did nothing, and then I get to a certain wavelength, electrons start jumping off. Matter of fact, if they made it more intense, more electrons per second were left off, And so that led him to believe that the electron had a nature that said, I can absorb light if it's a certain type of light. You can give me the wrong kind of light and give me as much as you want, and I'm going to ignore it. But if you give me a certain wavelength of light, I'm going to absorb it and be excited, and I'm going to jump away from the atom. Anyway, that led them to believe that light had this nature that was absorbed a bundle of energy, but it had to be the right type of energy, the right amount of energy, like that. Yes?
How did he regulate the wavelength that he was using?
I have, let's say, imagine if I was just doing the visible spectrum, I would need a machine that I could turn on red light, and that's a good question. I don't know. Could I make my own machine? I don't know how to do that. I could heat things up, and they might give off a color, and heat them up some more, and they might give another color. But that's a great question. I don't know. I couldn't make a machine. I have to do some more reading about that. How can I make my own machine that would give me one wavelength of light versus another? Right now, I could buy one that give me red light or blue light. I could buy one.
So it's not all it was just different colors?
Yes. Now, besides just the visible light, though, could we also use something like infrared, ultraviolet? And anyway, so any kind of light is available for the experiment, but maybe white light makes the analogy, at least you understand it's different colors. So anyway, he came up with this idea, and he said that, here's essentially what he said. He says that this electron, here's the nucleus, this electron, and it's really not going in a circle, by the way, I just drew it that way, but the electron here, if you give me a certain kind of bundle of light, I'll ignore it. Even if you give me a lot of those per second, you increase the intensity, I'm going to ignore it. But if you give me another kind of bundle of light, I'll absorb it and jump to a higher level. And matter of fact, I might even leave the surface of the metal and be gone. And if you give me more of those per second, more electrons will leave. And so it says, if you want me to jump from here to here, you need to give me an exact amount of energy, an exact amount. And they called that a what? A quantum. That's a quantum of energy. And so the theory then came up that if you had, for example, red light, he had a name for the particle that acted like a wave. And they say that light travels in little bundles of energy called photons. And so a red photon would have less energy. I don't know how to draw this. That would have this much energy, but a blue or violet photon would have more energy, like that. And so they'd have, each photon of light would deliver a certain amount of energy per photon. So any amount of blue light per photon has more energy than any photon of red light. And we found out that the atom has a nature, and give me 30 more seconds. It has a nature, it says, I will not jump halfway to that next level. It's a threshold. If you give me that full quantum, I'll jump. And I might even jump and leave the surface. If you give me the wrong kind of light, I won't make that jump. I thought that was pretty amazing that they discovered that, number one. So anyway, that's what's going to get us started on the idea of the quantum model. If you have a chance tonight, just kind of look over some of this. I'm going to circle some things, and I would be a little light on a test. I might be a little light on mathematics. I might only have like 3 or 4 problems at the most. And so if you want to just look at the typical problem they did, and you want to write that down, I feel pretty certain I would let you use your notes on this next test. I might even do more than that. Than that. So, all right, let me go ahead, and if you last time I'm gonna do this. Maybe it's the last time. So we had a large variety of scores on that test, and almost everybody got the back part right. I did a good job on that. But I noticed what I did is I subtracted from 168 and made it 165 total. So besides the blockouts, I also didn't count the first question you missed, all right? So if you look up there, you'll see the top scores there. And I thought 4 of them were way up there, 154 and higher, that was up there. They had a nice big cluster there. And so we ended up having like 4 A's, 8 B's, 2 C's, no D's, 1 F, okay? And that's what we had there. By the way, I forgot to add Alan's. Alan did get a B, so we had 4 A's, 9 B's, so that's what we had there. So if you want to take it home and look at it, the only reason you'd be looking at it is because for your own interest. I won't be going over them. So if you pass those out, I'll pass out the answer sheets. So if you want to eventually staple these together and give them back to you sometime this week, you can take time and look at them. Okay. I don't know if I put the right, I think I put the right answer. Oh, that was nice of me. I actually, I put the correct answer next to it, because I didn't think I would see you until the day. I don't know how you did that. That was hard. That was not that easy to test. 172 out of 165. That's the bonus points on that. That was way up there, man. That was tremendous. All right, again, if you can staple that, if you don't have to staple it now, but I want you to look at it, and when you get sometime this week, give it back to me. All right, there's a staple right there, and I really am glad you're back. Really glad. Oops, sorry. I can't do it today, but if you have an interest in this test, you want to talk to me about it, I think Wednesday at lunch, I know I'm available, maybe even Thursday. Yeah. Good job. That was not that easy.
Yeah. Mr. P, can I still turn this in? I had it down there.
Ah, that's why I put a 1 down. Okay, let me, okay. You didn't want to turn it in? You didn't want to turn it in on the day of the test?
And I did have a couple of others, like, more questions that I didn't finish, so I was like, oh, I'll get that in, I'll turn it in to him at the end of the day, and I forgot.
Okay, all right, thanks for doing that.
Thank you.
That actually is at UC Berkeley,
Yeah, okay, bro.
I mean, you don't have to do it right now,
You
but
could, okay, what I do is, if you just, I'd like to have it back, or you could, if you wanna make your own copy, you can, but it's the only one I have.
okay.
See the, Emily Massinger, I don't know if you ever heard of Massinger.
Yeah.
Okay, she's the one that actually looked this up for me. But, thank you.
Or can I go make a full copy while we're waiting?
Yeah, if they'll do it. It's many pages though.